decibels, more or less by definition.
The eardrum vibrates by a few picometers. That's trillionths of a meter. It's smaller than most atoms.
So one wonders how, just the membrane vibrating this ridiculously small amount can send reliable signals into the ear. And the internal workings of the ear that I'll describe in more detail, they vibrate by a few tenths of 1 nanometer. So this is about the size of a typical atom. So once again, how does something made out of proteins and lipids and whatnot reliably respond to such incredibly small stimuli? The third characteristic that's amazing is what's called a dynamic range of hearing, the breadth of stimuli that we can accommodate. So from 0 decibels, the threshold, to 120 decibels, which is about the loudest sound we can tolerate without any damage. That represents 6 orders of magnitude. In other words, a million-fold range in the amplitude of the sound, or a trillion-fold range in the power of the sound. And I don't know of any other kind of detector that can seamlessly accommodate a trillion-fold range of its inputs, but our ear can do that. So that's half the motivation. The other half of the motivation is pretty obvious. It's the clinical motivation. In our society, in this country, about 10% of the population have functionally significant hearing problems. And by that, I mean problems with hearing that affect daily life. For example, interference with the capacity to talk on the telephone or to understand speech in a crowded environment, and so on.
Or those for testicular or ovarian cancer, such as cisplatin. Those drugs happen to devastate the cells of the internal ear. So sometimes it's a life or death decision to use those drugs, but as a consequence, a patient may lose some or all of his or her hearing. There is damage to the ear from simply exposure to loud sounds, so-called acoustic trauma. And this can occur in an industrial setting. It used to occur a lot at airports before OSHA got there and put earmuffs. In our hearing faculty as we age. By age 65, about a quarter of us have some significant degree of hearing loss. By age 80, it's half. And this problem probably is a compound of daily damage from sounds in the environment. It's less obvious in Santa Barbara than it is in New York. people of the middle years of life, abrupt and unexpected hearing loss, which can happen to any of us tomorrow from viral infections, can really be devastating. Helen Keller, who's of course both blind and deaf, said that blindness deprives us of our contact with things, but deafness deprives us of our contact with people. And we are so social now that the daily minor, what seem like minor interactions, your conversations, you came to the door, chatting with people you don't really know. And if one is deprived of those inputs, one feels a strong sense of isolation that hearing people just cannot really appreciate. The other thing we lose with deafness is a distant early warning system. You know that if there is a tsunami alert, if there is a fire or something else, or even a car just screeching down the road, you're warned of it some time before the problem gets there. And again, a person who doesn't have the hearing capacity feels a vulnerability that they never had. So, in this talk, I'm going to briefly tell you what our ears are doing right now, how hearing ordinarily operates. Then I'll introduce you to the cells that do the work, explain something about their remarkable cause, and I'll spend the bulk of the lecture talking about what lies in the future, what's being done now at the program in which I'm participating, and what we anticipate in future years, particularly on the clinical side with dealing with these problems. So let me begin by telling you something about what your ears are doing right now. It's 2.5 seconds long. If you record it coming out my microphone, you can see pulses representing the different syllables that I'm speaking. This is my voice, and it's represented below in the so-called sonogram. This is the same information, but now it's broken down in terms of frequency. So the low frequencies are down here, higher frequencies are up here. And you can see there are characteristics such as the sound of prominent low frequencies or these wispier high frequency notes. And this particular bit is my voice. It's the last line of Dylan Thomas' poem, Fern Hill. As I was young and easy, in the mercy of his lead, time held me grief and time, though I sang in my chains like the sea. So this is though I sang in my chains like the sea. And you can see these low frequency stacks or vowels. So ang, this is my, this is my, chains, and so on. And the high frequencies are the consonants. Sang, chains, see, and what have you. And I show you this to remind you of the fact that you have to do this thousands of times a day. I'll use 53,000 phonemes or speech sounds in this particular lecture, and you'll get most of them right. And it's routine. You never think about the fact that during a given day you do 500,000 of these speech sounds, and very few of them. So most here has to, on the fly, break down the complex sounds and decide when the difference between the sound and the sound other sounds based just on the particular design of different frequencies that happen to be present. And we're very sensitive to frequencies. I'll give you a short demonstration of that. These will be frequencies that will play and slowly change as we go through a particular time. And then vary it by some amount. And you can listen to this here. So we're going to 182% change in frequency. Let me show you the other. Half a percent. You can hear this. 2%. Gets way off. And finally, 24% to 10%. String, as you can get this.
1/30th of the difference between two tones on a piano. And this very exquisite frequency sensitivity is what allows us to break down complex sounds, to distinguish one voice from another, and to distinguish other sounds in our environment. The apparatus that does that is the cochlea. The name cochlos is the Greek for snail, for obvious reasons. This is a coil structure with about 3 coils. It's about 8 millimeters in diameter, so it's the size of a chickpea or garbanzo bean. It's part of the labyrinth, and the rest of the labyrinth is involved in the apperception of accelerations. So there are 3 semicircular canals, here, here, and here. These are what give us our sensitivity to angular accelerations, or rotations of the head, or rotations of the body. And there's also something called the utrophil, which is here, and the sacculus here, which are sensitive to linear acceleration, including the acceleration owing to gravity. So I can tell which weight is down, because this organ is constantly active. And if I side like that, the organ, the utrophil, detects that and allows me to keep upright and know where I am in space. All of these organs have a common embryological origin, and they all use the same type of receptive cell that I'll introduce in just a moment. Now, to give you some idea of how this cochlea works, I want you to imagine unrolling this 8-millimeter spiral into a straight tube. It would be about 30 millimeters long. That's 1.5 inches. It has bone around its outside. Inside, it's filled with liquid, and there's an elastic partition called the basilar membrane running down its length. This is attached to the external and the middle ear. So here's the eardrum, which vibrates in response to sound. And then there are the 3 smallest bones in the body, the hammer, anvil, and stirrup, or malleus, incus, and stapes, that communicate this vibration to the ear. And the last of these, the stapes, has a piston-like quality, so it can compress or rarefy, pull out on the liquid in the upper compartment. So let's imagine that there's an increase in sound pressure, which is the compressive phase of a sound wave. Move the 3 bones to the right, and the last of them, the stapes, would push on this fluid and compress it, forcing this basilar membrane downward. I should say that the fluid in the lower compartment causes this other extensible membrane, the round window, to bulge outward. During a rarefaction, the other half of the sound wave, exactly the opposite happens. Everything moves to the left, the membrane is pulled up. So if this membrane were simple and homogeneous, you would expect it to oscillate like a violin string, the whole thing bouncing as one. And one can detect what actually happens by a rather sensitive technique, making a very tiny hole in the wall of this and using interferometry, shooting a laser beam in, bouncing it off this basilar membrane, and then measuring the reflected light to measure how the oscillation looks. And when you do that, one finds that this is not a simple string. It's sort of a magical string instead. It's a string that's broad and floppy at its top, that is at the apex of the cochlea, so that low frequencies cause vibrations there. It's taut and narrow at the base, so the highest frequencies, 10 kilohertz, cause a vibration there. And the other frequencies are represented in between in a logarithmic progression. So the real secret of this device is what's shown at the bottom. If you listen to a complex device like my voice, or like the piano or any other instrument, this system breaks down the various sounds into their component parts. In other words, the high frequencies will be represented here at the base, the middle frequencies here in the middle, and not lowest frequencies at the top. Helmholtz first realized that this device undoes the work of a piano. Right? A piano has a series of independent strings, each producing a particular note. And what comes out is an admixture of those, a nice melodious sound. The ear undoes that work. It breaks down the sound that it hears and then represents each of the notes at a different position along the length. Here's a dramatization